Okay, that's the logistic regression equation. That's our dependent variable, probability of success. And our independent variable is age. And beta 0 and beta 1 are the coefficients that we have to estimate in the model. Just like in linear regression for a straight line, we estimate slope and intercept. Now these are no longer slopes and intercepts of a straight line. They are parameters of this slightly ugly nonlinear equation. But we'll see how they're interpreted shortly. So once we have that equation and we have our data, we can estimate beta 0 and beta 1 from the data. Now, we're not going to talk about today how that estimation occurs. For linear regression, 2 weeks ago, we saw that there's an analytic expression that will give you the intercept and the slope. Remember, it was like sum of xy minus sum of xy squared over blah, 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 blah. There was some equation that would just give you the slope and the intercept. The same is true for multiple regression. When you have multiple x variables, there's also, it's now a matrix equation, but it will give you beta 0, beta 1 from the data. For GLNs, like at least for linear regression, logistic regression, there's no analytic expression that will give you beta 0 and beta 1. You have to use slightly more sophisticated techniques to estimate those values. And for anyone that's interested, the technique that's used most of the time is called maximum likelihood estimation, MLE. So if you're keen on looking into this more, go look up MLE, maximum likelihood estimation. It's an iterative technique where you make a guess, you try it out, and on the basis of how good or bad that was, you adjust your guess and you try it out again, and over multiple rounds of guessing, you end up with the best estimate of beta 0 and beta 1. But we're not going to talk about that beyond what I just said. Through some magic process called MLE, you estimate beta and beta 0, beta 1 from the data. And once we have those coefficients, then we have our model. Now we can plug in any value of age, just run it through this equation, and we get the predicted probability of success. So that is our model right there. So, for example, if we wanted to predict survival of a 30-year-old, that's our model. We would just replace age by the number 30, and we would do the math. E to the power of beta 0 plus beta 1 times 30 over 1 plus e to the power of beta 0 plus beta 1 times 30. And we get some probability P. And that's the model prediction. So doing the math for a model prediction is slightly more complicated than linear models in the straight line, just because it's a sigmoidal equation. We can fit a logistic regression model in R, not using LM, which we used last week for a linear model, using GLM for generalized linear model. We have to give the GLM command this extra information. Family equals binomial, and then bracket length equals logit. That basically supplies the GLM function with those pieces of information that we have to have in order to do a GLM. A distribution that we're assuming for the dependent variable, binomial, and the form of the link function that we're going to use to link the linear equation with the nonlinear dependent variable, logit. And just like linear models, we have the dependent variable here, status, and then a tilde, a little squiggle, and the independent variable in our data frame, and then it does it. And we can use summary to look at the output. And just like linear regression, we get our coefficients, the intercept, which is beta 0 in our notation, and age, which is beta 1 in our notation. Then we get a t-test, or actually a z-test, not a t-test, on each of them. And then some weird stuff down below, including an AIC score. Do you remember what AIC is used to do? What is AIC? Yeah.
It calculates how well the prediction fits the data or something?
That's right, yeah, it's a measure of the model fit, exactly. And are big AICs better or small AICs better? Do you remember?
Smaller.
That's right, smaller values of AIC mean a better fit. And it's a type of model fit that takes into account the number of parameters in the model, right? So it trades off model fit with complexity. Good. So we're going to talk about how to interpret those estimates, because they're no longer an intercept and the slope of a straight line. They're now beta 0 and beta 1 in this slightly complicated logistic equation. Now, just a little shorthand. For binomial family, logit is the default, so you can actually leave it out of that command if you want. You can just say family equals binomial. Now, it's just my personal preference. You can do whatever you want in the course, it doesn't matter. But just to say, my personal preference is always to keep it in there, in part to remind myself of what I'm doing, and in part so that there's no question about what R is doing. Default values of things are nice because they make it so you don't have to type as much stuff. But the downside of default values is that that information is hidden for you as a programmer. Okay, so let's talk about what these coefficients mean. So here's what the data look like for males and females combined, with age on the horizontal and probability of success on the vertical, probability of survival, and the blue line is our logistic regression fit. And so this is the model. Log p over 1 minus p is equal to 2.07. That's the intercept, as it were, minus 0.7 times age. The age estimate is 0.07. So that's our equation. We can rewrite it in terms of p. So p, the probability of survival, is equal to e to the power of 2.07 minus 0.07 age over 1 plus e to the power of 2.07 minus 0.07 age. So that's the equation that determines this blue line that corresponds with that blue line. So it's no longer a slope or an intercept. They're related to this. They're related to the slope and the position of that line, but not in a straightforward way. Yeah.
Do you prefer which equation you use?
Oh, this one or this one? Well, in a way, it doesn't matter. You're not actually going to be using the equation as it were. When we ask R to give us a predicted probability, we're just going to use the predict function. We're not going to have to actually manually type that equation in. I'm just thinking, I don't think I'm going to. I don't think it's there. But if I were to ask on an exam, write down the logistic regression equation, it wouldn't matter to me which one. And I would probably say, write the equation for logistic regression in terms of the probability p, not in terms of log p over 1 minus p, or something like that. Yeah. But I'm not going to ask you to recall equations on exams. I think we're beyond that now. Okay, so, but I am showing the equation here just so you understand how logistic regression works, and it's going to help us understand how to interpret those coefficients. So that blue line is equivalent to that equation, or this one. They're the same equation, just expressed differently. In R, we don't have to actually use the equation directly. We can just use the predict function, just like with linear models last week. If we feed our predict function the model object that was fit with GLM, MindMod, and then some new data in a tibble or a data frame that we created. Now we have to say type equals response. This is a little bit of complexity that I don't want to talk about, but the predict function in R can give you different flavors of predictions. And the one we want is called response. That will give you the predicted probability of survival. You can look at the help function for predict and GLM to see what other types R will give you, but you don't need to. So when you want type as response, and that gives us 0.295627. So a 30% chance of survival for someone who's age 40. Does that line up? Yeah, it does. That's age 40. And if we draw a vertical line up from 40, where do we hit the blue line? Yeah, right there, 30%. So that's giving us the location of that blue line at age 40. So really, I've showed you a whole bunch of crazy equations and lots of complexity. The bottom line, end of the day, story is this slide. That's how you actually do it in R. You just use GLM instead of LM. You have to say family equals binomial because the dependent variable is binary. And then, just like a linear model, you can use the predict function to get predicted values. But instead of a straight line, our model function is a sigmoid function, a logistic function. So next I want to talk about how to interpret those numbers, those parameters, like 0.07 for age. But before we do that, are there any questions I can answer? No? Okay, if you change your mind, just raise your hand. So how do we interpret these parameters? With the linear regression, the beta 1 exon parameter, the beta 1 parameter was literally the slope of the line, right? It was the change in the dependent variable with a unit change in the independent variable. How much you changed in y when you changed in x by 1. That's not the case here because we have this more complicated nonlinear equation of P. So the regression coefficient of a variable, like minus 0.07 here for age, that corresponds to the change in log odds. What is log odds? Well, it's log because it's a logarithm here. And what does odds mean? Yeah.
It's a ratio, so the probability of any events that happen to...
Yeah, it's a kind of a ratio. Odds refers to the relative probability of one event relative to another event. So if the odds of something is, if the odds of survival versus death is 2, that means it's twice as likely to survive than it is to die. It doesn't tell you what the probabilities are themselves, it just tells you the relative odds of one over the other. So in this form of the model where we have log p over 1 minus p on the left, the coefficient on age corresponds to the change in log odds. The change in the log odds of survival with a unit change in age. In the exponentiated form, which is this one down here, we just have p on the left and the exponential form on the right. Now, the coefficient on age corresponds to the odds ratio. So, the thing to sort of remember always with logistic regression is the coefficients are in units of log odds. They're not in units of the dependent variable, like they were in ordinary regression, in linear regression. Right? In linear regression, those slopes are in units of y, whatever that is, because they correspond to how much y changes in units of y for a unit change in x. Here, they're not in units of y. They're not in units of p. In this form, they're in units of log odds of one of the outcomes relative to the other. And in this exponentiated form, they're in terms of the odds ratio. And we're going to unpack this a bit and see how it works. So the interpretation for a coefficient, like this one on age, is the change in log odds per unit change in the predicted variable. For every increase of age by 1, you get this much change, minus 0.07 change in the log odds of survival relative to death. So we're going to plug in some numbers and see how this looks. So here the coefficient on age is minus 0.07. That means for each additional year of age, the log odds of survival decreases by 0.07. Okay, is that good? Is that bad? I don't know. It's kind of hard to get a handle on what a log odds change is. How big is big and how small is small. In this form, the exponentiated form, we would say the odds ratio of survival for age plus 1 versus age. So the log odds of survival for someone who's 1 year older than someone else, so a unit change in age, is 0.93. That means the person who's 1 year older has a 93% chance of survival relative to the person who's not 1 year older. So an odds ratio greater than 1 means an increase in odds of survival. An odds ratio less than 1, like here, is a decrease in odds of survival. Now, this is not the same as, 0.93 decrease in probability of survival. It's a 0.93 odds ratio of survival. So why is it 0.93? Anyone know? If the coefficient is minus 0.07, how come it's 0.93? We'll see in the slide or two. Okay, so let's talk about odds versus probability. The odds of an outcome is the ratio of the probability of the outcome to the probability of the opposite outcome. So the ratio of the probability of heads versus tails, or survival versus non-survival. So it's p divided by 1 minus p. So the probability of survival is 0.8, and the odds of survival is 0.8 divided by 1 minus 0.8, which is 0.2, which is 4. So if the probability of survival is 0.8, then the odds of survival is 4. So that's how the two of them relate to each other. The log odds of an outcome is the logarithm of the odds. I said natural logarithm. Do you remember the difference? Do you remember what a natural logarithm is? Yeah, what?
Base.
Yeah, it's a logarithm in base e, Euler's number. The other kind of logarithm you probably dealt with in school is log base 10, right? So what's the log base 10 of 100? 2. That's right, because 100 is 10 to the power of 2. The log base 10 of 1,000 would be 3, because it's 10 to the power of 3. I told you it would come back to haunt you. Actually, I didn't tell you. Someone told you it would come back to haunt you. So let me just write it on the board something that you should remember in your travels going forward. In high school, you probably saw log and then ln, right? Those L's. So this you probably called log, and this you probably called ln, or something horrible like that. They're both logarithms. This is usually in high school what you refer to as log base 10, and that really is what you refer to as log base e. Okay, so ln is just log base e. Basically, from now on in your undergrad, when you see log, it's referring to log base e. Log base 10 is really only something that you do in high school to understand what a logarithm is. Because it's easy to understand what 10 times 10 is, and 10 times 10 times 10. You just keep adding zeros. If you were to teach logarithms in high school using log base e, then you'd have to get people to do 2.7 times 2.718 times 2.718. I don't know what that is. Jesus, who knows what that is? That would be cumbersome. So that's why you learn about log in base 10. But really, it's very unusual in math, in the sciences, to actually use log base 10. Most of the math you'll see that involves logarithms is log base e. And it's not, and people don't say log anymore. They just say log. So jettison log from your brain, and remember when someone says log or logarithm, it's log base e. Sorry. I don't know why they don't tell you that in high school, but it's a theme of undergrad, whether it's in math or usually it's in the sciences, chemistry or physics. Often a class will start and the professor will say, okay, so remember when you learned about this? It's not really like that. That was wrong. It's actually like this. And the this is a little more complicated. All right, that was off topic. So if the probability of survival is 0.8, then the odds is 0.8 over to 0.2. The log odds is the natural logarithm of the odds. So log of 4, log base e of 4 would be 1.39. And that's the odds ratio. So 4 is the odds. 1.39 is the log odds. And the odds ratio is the ratio of odds between two situations. So the coefficients of a logistic regression model are the change in log odds per unit change in the continuous variable of age, or equivalently, a change in the log odds across categories of the independent variables category. So going back to our example, and then we'll take a break. The coefficient for age is minus 0.07. There it is, minus 0.07. So those are our logistic regression equations. It's the same equation, just expressed in two ways. So what this minus 0.07 means is that for each additional year of age, the log odds of survival decreases by 0.07. Or, equivalently, if we use this form, the odds ratio of survival is e to the power of minus 0.07, which is 0.93 for an additional year of age. So plus 1 unit of age corresponds to a 0.93 odds ratio of survival. So it doesn't matter if you're comparing a 20-year-old plus a 21-year-old or a 90-year-old with a 91-year-old. For any location along that age axis, the odds ratio of survival for an age versus an age plus 1 is 0.93. And that seems weird because, like in the linear model, yeah, no matter where you are on the horizontal, the slope of the line is the same. Here, the slope of the line is not the same. But that's fine, because we're not saying the slope is the same. We're saying that the odds ratio is the same. And the odds ratio, a ratio is a nonlinear thing, and that's why it's the same across the range. So plus 1 unit of age is 0.93 odds ratio of survival. And the thing to remember is that an odds ratio greater than 1 implies a positive association between the predictor and the outcome. That means an increase in the predictor is an increase in the chance of survival. If the odds ratio is less than 1, that implies a negative association. An increase in the predictor variable corresponds to a decrease in the odds of the outcome. Okay, that's a perfect exam question. Hint, hint. Odds ratio above 1 or less than 1. I'm not going to ask you super fine-grained details about all this odds, log odds, odds ratio stuff, but I might ask you that. An odds ratio greater than 1 implies a what? Positive or negative association? Now, the intercept of the logistic regression model, we're not actually really interested in. Usually, it's really the coefficient on each predictor variable that we're interested in. Because that tells us the relationship between the outcome and the value of that predictor variable. In this case, it tells us that older people are more likely to die. How much more likely? Well, for every extra year of age, you have a 0.93 odds ratio of survival relative to someone who's 1 year younger. Okay. Questions so far? Or we'll take a little break. 5 minutes-ish? Yes, question.
If you're doing like p over 1 minus p is negative.
This one?
Yeah, would it be 1 plus p because it's negative already? Minus negative.
So the question is, because you're saying because this is negative?
Yeah.
Would you do 1 plus p?
Yeah.
Not, I don't think so, because this part, in this form of the equation, this part ends up here. So, I mean, if this was positive, then this would be a positive here. It would be plus. But that doesn't really change this down here. Yes?
Does that negative still matter?
No, the negative sign definitely does matter. Because e to the negative 0.07 is different than e to the positive 0.07. The negative sign here implies that age has a negative association with the outcome.
Oh.
Yeah. Yeah.
Earlier you talked about plugging in different age values in order to get
Yeah.
P.
Yeah.
We do the reverse where we have P and we try to predict the age.
Yeah, so the question was, we talked about how to take a particular age and predict P with probability of survival using the model. And the question was, can we go in the opposite direction? Can we say, at what age would there be a 50-50 chance of survival? Sure, we certainly can. Yeah, if we can just do the algebra and invert that equation.
Could there be multiple ages that have the same P though?
Yeah, that's a good question. Could there be multiple ages that have the same probability? So I'll answer it indirectly. So the sigmoid function is bounded by 1 and 0. And it's also guaranteed to be monotonic. Do you remember what monotonic means for functions? Anyone?
Isn't linear regression monotonic as well?
Linear, yes, linear regression, straight lines are also monotonic.
Does that mean just only one X for every Y?
Yeah, essentially it means only one X, for a given Y. Monotonic means the slope of the function never changes. It never, the sign of the slope never switches. So if the slope is positive, it can be a little bit positive or a lot positive, but it never goes negative. And vice versa. I guess that doesn't relate to multiple X. The answer is no. You can only have one age for a given probability.
And that's because of the prediction, not necessarily the actual.
Yeah, it's true. Even if the function wasn't monotonic, even if it went up and down, the point is it never reverses on age. You can only have one. You can only have one. There's only one age that corresponds to a given probability. No, I guess it's true. If it was non-monotonic, like let's say the function went up and then it went down again, then it might cross the 0.5 line once over here and then again over here when it went down, right? Up and down. And then you have two ages that correspond to 50%. But it can't. It has to be monotonic. So I'm going back to my original position. Monotonicity guarantees that there can only be one X value for a given Y value. We need to take a break. Okay, let's take a 5 to 7 minute break.